So I'm going to continue in derivations and applications of Greek letters. So last time we talked of Greek letters, we covered delta. We derived the delta for a call option. For a put option, I gave you the equation. We talked of a delta neutral strategy. Okay, let me explain to you what is a delta neutral strategy. So when you're hedging the risk, suppose I give you ST is equal to 100 and the call price is 10 and my delta is 0.4. I want to buy 1,000 shares at maturity time point T. The final institution should buy 0.4 times 1,000, which is 400 options. Therefore, ST will be increasing by $1 every time, and the call price would be increasing by $0.4. There is a gain of $400 in stock position and $400 loss in option positions, such a way that the total payoff is zero. And then you have Black's calls for an EU call option and a put option and a dividend paying capacity. So I'll give you the equation for CT and PT, where you have a new variable which is being introduced here, which is the dividend, yield. Okay, Q being the dividend yield. So that's for the call option, and that's for the put option. Now the equation for D1 and D2 are listed here, and you're going to use it in your derivations. When the first partial differentiation of the accumulated normally distributed D1 is given as shown here, and for D2 it's derived as such. So delta being the change of the call option with respect to stock price. So you need to derive it, and you plug the equation from what I've said here. That is the Black's cause for a EU call on a dividend paying capacity. You plug the equation here, and you just start deriving. So this is a partial derivative here, and you have to differentiate with respect to ST. So we're using here product differentiation, whereby you differentiate with respect to ST, and the other product differentiation, given the fact that the accumulated normally distribution of D1 is a function of ST, it turns out to be like this. You break the differentiation as such. Okay, and the same thing when you have to differentiate the accumulated normally distributed variable of D2, it becomes like this, and you just continue the derivative. And you will get the delta of a call to be listed as such. And then I have the theta, the rate of change of the option price with respect to the passage of time. All right. So these are the equations involved in the derivation of theta. Okay, the rate of change of option price with respect to t. So theta is negative. And then there is the Greek letter gamma, which is the second partial derivative of delta, where you have a change in option value. Okay, which is listed as such. So these are the things that you can derive: modify duration and convexity. And yeah, up here for today, and we'll continue with Vega in the next video.